Welcome back to the continuation of part 3 of week 5. I've just finished the discussion of the different definitions of rate coding. Rate coding is linked to the idea of stochastic firing. Stochastic firing can be described by a Poisson model, and the Poisson model is the topic of this video. So we have seen that there are all these different definitions of rate coding, and I would like to convince you that if you think of a rate code where the exact timing of a spike doesn't play a role, where spikes can jitter a little bit, then a Poisson model is an appropriate description. So what is a Poisson model? Suppose I have observed a spike train. We assume that during the whole period, big T, the neuron fires at a constant rate. This is called a homogeneous Poisson process. Now we discretize time, so we use short time bins delta t. And then we say, well, if the neuron fires at a constant rate, which I call rho 0, then the probability of finding a spike in such a small interval is just rho 0 times delta t. In other words, if I decrease my temporal resolution, if I take smaller time steps, like this, so now delta t, the new delta t, is smaller, then the probability of finding a spike in one of these segments is also smaller. This is expressed by this relation that the probability is proportional to delta t. For very small delta t. So let's describe this more formally. So I'd say the firing probability is in a time step delta t is Pf. Now I'm interested in mix, but Pf will depend on delta t. I'm interested in a definition which is independent of delta t. Now, if delta t is small enough, then Pf is proportional to delta t. So formally, I can define a rate by the limit delta t to 0 of the measurement Pf, the measured probability of firing of spike in delta t. I divide by delta t, and this would provide me with an estimate of the firing rate, rho 0. So this is the rate of my Poisson model. Let's suppose now that we have a model, and this neuron model is a Poisson process. So it really fires in each time step delta t with this probability. And so it has fired here. This is the moment when it has fired. And now the question is, can I calculate something like the interval distribution? So given that it fired here, what's the probability that it survives for all this time up to here without firing? Survive without firing again. Now, instead of considering a single neuron, let's for the moment switch to a group of neurons. So I have here my group of 500 neurons, say, and for some reason, because I stimulated them or whatever, I manipulated such that all 500 neurons have fired a spike in this moment in time, in this little time step. And I ask, what's the probability that they survive up to for a certain duration t? Now, this probability of surviving will decay. Well, S is the fraction of neurons that have survived up to time t. Well, they decay. At each moment in time, there's a certain rate of firing, which corresponds to a decay of the fraction of neurons that still survive. So the probability to survive will decrease according to this differential equation, and the solution is S of t, the fraction of neurons that survives from that group that has fired here, is e to the minus rho times t. All neurons have fired here. The probability to survive at 0 in the same time step is 1. So the condition is that S of 0 is equal to 1. So this probability to survive is completely analogous to the case of radioactive decay. I have a large group of particles. They have a certain decay rate. This is my rho. And because of this spontaneous decay, the group that still survives will decay exponentially. This is the continuous time description. But we can do the same thing also in discrete time. So the probability to fire in a small time step is rho 0 times delta t. So the probability to survive in this first time step is 1 minus rho 0 times delta t. The probability to survive in the second time step is the same thing. The probability to survive in the third time step is again the same value. So it has to survive during the first time step, then it has to survive during the second time step, then it has to survive during the third time step. So the probability to survive without firing for 3 time steps is the product of these individual terms. It's a product because firing or not is an independent decision for a Poisson process at each moment in time. More generally, the probability to survive for n time steps for homogeneous Poisson process is simply 1 minus rho 0 delta in brackets to the power of n. Now, the survival time t is n times delta t. So I can write n as t over delta t. So S of t is 1 minus rho 0 times delta t over delta t. I put in the t that I forgot, so it's delta t, it's delta t. Now, I can take the limit delta t to 0, and this, using the definition of the exponential, leads exactly back to this formula here. Thus, whether we start from discrete time or whether we work immediately in continuous time, we can calculate the probability to survive, also called the survivor function. Now, the homogeneous Poisson process is a special case. We may also assume that the rate changes. So in the first time step, I have a rate rho of t1. In the second time step, I have a rate rho of t2. In the third time step, I have a rate rho of t3. For the moment, we assume that this rate is constant during that time step. So I evaluate at some moment in time, and then multiply by delta t, and then this gives me again the firing rate for this time step. So in an arbitrary time step, tk, pf of t is rho of tk times delta t, the time step at time t. Repeating the argument that I made on a previous slide, it's easy to see that we find again the exponential function, but now it's this time-dependent rate. The rate may be different. Suppose a first spike occurred here, then I have a rate rho of t, which changes. We may go up, which may go up and down. If I want to know what's the probability to survive up to some time t, well, I just integrate over this function rho of t prime from t hat, that's the moment when the last spike happened, up to time t. In one of the earlier lectures this week, I pointed out the importance of the interval distribution. So what would be the interval distribution? Suppose a neuron has fired here. We ask the question, what's the probability that I would see the next spike over here? More precisely, it's the probability density to find the next spike at t, given the last spike has occurred at t hat. Now, for the neuron to have the next spike at t, you talk about an interval, it has to be the next spike. That means the neuron has to survive from t hat to t without firing. So I can take the expression I just calculated. But then it actually has to fire at time t, but the instantaneous rate of firing at time t is rho of t. So the interval distribution has an exponential term from the survivor function and then the instantaneous rate. With the notions of an inhomogeneous Poisson process, you can go back to definitions of the firing rate. Suppose you have a Poisson neuron model, inhomogeneous Poisson process, and it has a time-dependent rate, and you observe the total number of spikes accumulated over time t. Well, the Poisson model allows you to calculate this. Suppose that I make several measurements across different repetitions of the same stimulus. The PSDH is, in fact, an estimate of my instantaneous firing rate of the Poisson process. So the PSDH will be a noisy, discrete version which should in principle be very close to this instantaneous rate. In fact, if K is very big, you have 10,000 repetitions, and then you allow yourself to make delta t fairly small, then this becomes a very good estimator of the firing rate rho of t of the inhomogeneous Poisson model. Now we said that this is an experimental measurement. Now assume that I have a group of n neurons that all have the same time-dependent firing rate. Then the instantaneous measurement of the population activity A of t is again a good estimate of the underlying firing rate of the individual neurons. To summarize, for a Poisson model, for an inhomogeneous Poisson process, I can calculate different quantities. We can define an instantaneous rate, which is closely related to the experimental procedures of estimating a rate. We can calculate the interval distribution. We can calculate the survival function. And therefore, the Poisson model is a first important description of spike trains, of fluctuations in neuronal spike trains. In a Poisson model, firing in step 1 is independent to firing in step 2. A real neuron, if it fires a spike, it will have a dead time. It will be refractory. It's less likely to fire immediately afterwards. That's not captured by a Poisson model, neither by the homogeneous nor by the inhomogeneous Poisson process. Nevertheless, the Poisson model is an important reference model used widely in experimental and theoretical neuroscience. Before we continue, please have a look at the quiz.